Hi, I'm Nidhi Vespute, and this is the Group 11 for SER 502 presentation. Welcome to our demonstration of Noah, a simple programming language we designed and implemented for SER 502. Noah is entirely built in Python and covers a complete end-to-end pipeline from source text to executed output. As we move on to second slide, the assignment asked us to design a language with primitive types, operators, conditionals, loops, print, and assignment, and implemented a lexer, parser, and runtime environment. Noah addresses all of these. We have integers, strings, and booleans as our data types. The compiler is a handwritten regex lexer paired with a recursive decent parser. The immediate form is an abstract syntax tree with typed node kinds. The runtime is a treeblock interpreter with an environment store. And we have 6 sample programs covering every required construct. Next slide, please. Noah keeps the syntax familiar while covering all core requirements. We support 3 primitive value types: integer, string, and boolean. For operators, we have arithmetic with plus, minus, multiply, and divide. Relational operators less than, greater than, and equal to. And logical operators and or and not. Control flow includes if else, a ternary operator using question mark and colon, and both while and for loops. Output is handled with a print statement that works with every supported type. Here you can see a quick Noah snippet. We assign an integer, a string, and a boolean, then we print them.
I'm Gargi. Moving on to the next slide, we have the setup. So setting up Noah is straightforward. You need Python 3.8 or higher. No external libraries are required. It runs on Windows, Mac OS, and Linux. The repo is organized into 4 directories: source for the source files, data for the sample programs, and doc for documentation, and a README at the root. To run Nova, you just pass the source file as a single command line argument. For example, Python 3. Um, this satisfies the assignment requirement of invoking the compiler and runtime with one file argument. Next slide, please. Okay, moving on to the next, we have lexical analyzer, which is in alexa.py. It takes raw Nova source text and converts it into a structured token stream. The implementation uses a Python's free module with a single compiled regex that checks tokens alternatives in order. After scanning, a keyword map converts identifiers like if, while, print, true, and false into proper token types. The Lexer also tracks line and column numbers, which makes error messages much more useful. Here you can see a quick example. The input print of Nova semicolon gets tokenized into print, left parenthesis, string, right parenthesis, and semicolon. Next slide. Here are the core token categories. Number matches one or more digits. String matches anything between double quotes. Boolean matches the literal true and false. Identifier matches any name starting with a letter or underscore. Then we have operator tokens assigned for single equals, AQ for double equals, GT and LD for greater than, less than, and the arithmetic operators. There are 3 reasons this token system matters. It gives the parser a consistent vocabulary, it keeps keywords clearly separated from identifiers, and it provides location-aware diagnostics. If the lexer encounters an unexpected character, it raises a lexer error with the exact line and column.
Hi, my name's Bill, and we're going to talk about parser. Our parser lives in parser.py, and it's built using a recursive descent approach. That basically means we have one method for each grammar rule, which just keeps things clean and easy to flow. As it processes tokens, it uses an eat method. So if the token isn't what we expect, it throws a parser error. So mistakes get caught early on. The output of the parser is a tree made up of node objects. Each node has a type, an optional value, and a list of children. We also keep statement parsing and expression parsing separate to keep the logic organized. Operator precedence is handled naturally by how deep the function calls go. And at the top, we have ternary operators with the loosest binding. And as we go deeper, we move through logical OR and equality comparisons, multiplication, unary operations, and finally primary expressions, which bind the type test. So in practice, that means multiplication and divisions happen before addition and subtraction, and logical operators are evaluated last. The next slide. So here we can see the full grammar written in EBNF. A NOA program is just a sequence of statements. The statements could be an assignment, an if statement, a while loop, a for loop, print statement, a block wrapped in curly braces. Assignments uses a single equal sign, and if statement can optionally include an else branch. The for loop allows the usual structure, initialization condition, and update separated by semicolons. Expressions follows the same precedence hierarchy we just talked about, starting from ternary and working down to primary. One important thing here is that the grammar closely matches the AST structure, the abstract syntax tree structure, and the AST itself mirrors how the program is executed at runtime. Next slide. So NOA uses an abstract syntax tree, or AST, as the bridge between parsing and execution. Each node in the tree has a kind, a value, and a list of children. Some of the main node includes program, block, assignment, print, if, while, binary operator, unary operator, and ternary, along with the literal types like number, string, boolean, or an identifier. A key design choice we made is that the runtime only works with the AST. It doesn't look at the original source code at all. That keeps things modular and makes the execution phase much simpler. Next slide. Let's walk through a quick example. So for the small program, assigning 5 to x and then checking if x is less than 10 to print it, the parser builds this AST. At the top, we have the program node. It has two children's. First, an assignment node for x equals 5, and second, an if node. The if node includes a binary operator node for the condition x is less than 10, and a block node that contains the print statement. So at runtime, the condition evaluates to true. So the block runs and the output we get is 5.
Okay. Hi, my name is Disha, and I will be explaining from the runtime. So the runtime is present in the runtime.py file and is basically a tree walk interpreter. The interpreter class receives the root program node and walks the entire tree, dispatching to a specific method based on a node kind. The variable storage is handled by the environment class, which is a simple key value dictionary with the set and get method. The design has 3 key decisions. One is the exec method, which handles the statements and controls the side effects. The evaluation methods, which handles the expressions and returns the value. And the two are all strictly kept separate. Here are the execution semantics mentioned in detail. On the statement side, the exec program controls the overall program order. The exec assignment evaluates the right-hand side and stores it in the environment. The exec print evaluates and gives out the outputs, and then the exec if, exec while, and exec for handles all of the control flow. And on the external side, the evaluation methods returns the values. The evaluation binary op handles the arithmetic relation and the logic operators, and then the evaluation unary operators basically handles the not and the unary minus, and the evaluation ternary handles the conditional expression. One important detail is the and or use short circuit evaluation. So the second operand is only evaluated when needed. The booleans always print as a lowercase true and false, and not Python's capitalized true or false. We have like 6 sample programs covering every required feature. So the sample 1 covers the types and prints. Sample 2 covers if else. Sample 3 covers while. Sample 4 covers for. Sample 5 covers the ternary operator and all 3 Boolean operators. And then sample 6 was added specifically to cover the subtraction, multiplication, division, and the greater than operation. This is how you usually run the commands, and then you get the expected output for all the samples. So I will start doing the execution now. You'll find all the execution here in the README file. So you can just directly type it in. So as you can see in the sample 1, it basically types and prints. So we assign a value to x, which here it is 10, and then basically we ask NOVA if So the name is Nova again, and then we'll flag it as true if x is equal to, wait, I'm sorry. Okay, so we assign x is equal to 10 and the name equals Nova, and we flag it as true and then print each one. So we get 10 from the integer and then true from the Boolean in Nova's native lowercase format. So we are printing the name Nova here, and then we are asking whether x is equal to 10, so it flags it as true. So then we have a sample 2. So what here is what we asked is if else is basically used here. So we asked, we have assigned a value x as 5 and y as 10. So we asked and put in a condition that if x is less than y, then we print x is smaller. If that is not the case, we ask else, we ask it to print y smaller. So as you can see that x is smaller than y. So okay. So this is sample 3. We are using while loop here. So we start at 0. So we are starting the count at 0, and then the loop will loop while is in the counter. So which is so the counter will basically, when we write print, so the counter will print anything value that is less than 0 as per the condition. Sorry, less than 3 as per the condition. So we get the value 0, 1, 2, 3 here, and we can change it, and then the output will come as the same. Then we have sample 4. So in sample 4, we are showcasing the for loop. So it is just the same. Anything less than 3 is printed. So next we have sample number 5. So here we have the ternary and the Boolean operators. So we have assigned a value a as 7 and then b as 3. So we ask one of the condition, if a is equal to b, then we do not we get not equal to because of the ternary, and then false, and we'll get for this value, so we'll get false since a is not equal to b, and then in print it will give, and then we are going to print not false here. Sorry, the print value in the not false gives true. Yes, because 7 is not equal to 3, so it's not a false this thing. So we get that, and then here whether it is a true or false, we get true as a value because 7 is not equal to 3, and then here again we get true since we get false here because all three are as our Boolean operators since 7 is not equal to 3. We get not equal to for this as the result, we get not equal to, and then for print not false, we get true as a value, and for print true or false, we get true, and here we get false. So we have our last sample, which is the arithmetic grade. We have whether it is greater than or equal to, and then whether it's greater than or not, and then we also get the subtraction, the operators like the subtraction, the multiplication, and the division programs for this. So we have assigned x as 5 and y as x as 20 and y as 5. So if we run the sample, so we get the difference as 15, the product as 100, and then the quotient as 4, and then we also get the value that x is greater than y. So to summarize the entire thing, Nova is a complete end-to-end language implementation, the language which covers all the required data types, operators, conditionals, loops, and the prints. The compiler uses a handwritten lexer and a recursive descent parser to generate a clean AST. The runtime tree walks the AST with an environment store, and then the runtime safeguards it. And then we have 6 sample programs to demonstrate every feature. Thank you.